Right, hello everybody. For this physics project, we will be doing the first problem, which involves the turntable with the block, ball, and pulley system on top of it. So to start off, first of all, we have the turntable, which has a radius of big R, and on top of that is a block with mass M, which has a string going through it over a pulley, and at the other end of the pulley there is a hollow ball, which we have given a mass of little m. Now, as that block, pulley, and ball system moves, that's going to cause the turntable to rotate. And in this case, we're trying to determine what is the angular speed of the
We're
turntable.
going to need some formulas to solve for the angular speed of the turntable. We can start with Newton's second laws for the net torque and net force. We're going to use that the net torque is equal to the magnitude of the radius and the magnitude of force times the sine of our angle, theta. We're also going to be using that net torque is equal to the moment of inertia of a mass times the angular acceleration. And we're just going to use force net equals the mass times the acceleration, and also that our net force is equal to the sum of all the forces acting on that object. For our moment of inertia, we're looking at it for a hollow sphere, which is given by 2/5 times mr squared. And then we're also going to be using centripetal acceleration, which is given by v squared over r.
Alright, now before we can start solving the problem, we have to understand the forces involved here and how they work. Now we're going to do that by doing a free body diagram, which starting with the block sitting on top of the turntable here, we have the normal force acting straight up off the block, and then we have the force of gravity counteracting that, pointing straight down. And additionally, because the block is attached to the rope here, there is a force of tension from the rope pulling on the block, pointing to the right in this case. That goes all the way down onto the pulley to the hollow sphere here, which has also force of tension acting in the same direction as of that cable there, pulling it on up. And we also have the force of gravity, which is causing the hollow sphere to fall down. And another note that we just didn't elaborate on earlier is that this entire turntable here is frictionless, meaning that there isn't a force of static or kinetic friction acting on the box here. Alright, so now we're going to be calculating the angular velocity for the turntable. Now in order to do that, we're going to start by finding the force of tension here by using the two equations for torque about the hollow sphere. Now, the first equation for torque we're going to be using is moment of inertia times the angular acceleration. And the second equation for torque we're going to be using is the radius times the force of tension right here, which we need to solve for, times sine theta. Now in this case, sine theta is actually equal to 90. Well, the theta is equal to 90 because the angle between the rope as it goes about the pulley, we're assuming that's 90 degrees here, which actually means that sine of 90 is equal to 1, which means that when we relate the moment of inertia times the angular acceleration to this bit here, the other equation for torque, the sine 90 just is 1, so that cancels itself out. And using the moment of inertia for the hollow sphere we established earlier, we get that relating the two torque equations, we get 2/3 the mass of the hollow sphere times the radius squared times the angular acceleration is equal to the radius times the force of tension, which we're trying to solve for here. Then so for the problem here right now is that we have this angular acceleration bit. Now in order to get rid of that, we know that the angular acceleration is just equal to the acceleration divided by the radius. Sub that in here, divide by r. After mixing all those things around, we eventually find that the force of tension is equal to 2/3 mass times the acceleration. So that's our first bit, finding tension. Now our second bit here is going to be finding the acceleration of the system. Now in this case, we're going to be using the F equals ma to find the acceleration here. So starting off, we find that the net force, this is again about the sphere here, is equal to the mass times the gravity minus the force of tension. Now, if you recall just a second earlier, we actually solved for the force of tension, which gives us that the mass times the acceleration is equal to mg minus 2/3 ma. Now, after doing some rearranging here, adding the 2/3 mg to the other side, dividing by mass, we eventually find the acceleration is equal to 3/5 times gravity. Now, getting close here. And then using those two equations, we can relate the force of tension with the new acceleration that we just found. So plugging in that new acceleration value, we find that our fully solved force of tension here is equal to 2/3 mass times 3/5 times gravity, which eventually simplifies out to 2/5 mass times gravity. Now, to finally solve this whole thing, we're going to once again say that the net force is equal to the mass times the centripetal acceleration about the big block here. And the reason we can relate the big block to the turntable in terms of angular rotation is because since the block is on top of the turntable, when it moves and eventually has angular rotation and momentum, that's going to be the same for the block here, which is sitting on top of the turntable, as the turntable itself, because they're both part of the same system. Now, moving on from that, we have the centripetal acceleration here, but we don't need centripetal acceleration. We need to find the angular velocity. Now, in order to do that, we rearrange the equation a bit, simplify some things out. We eventually derive that the centripetal acceleration is actually equal to the angular velocity squared times the radius. So now, to finish up, final step here, we say that the net force is equal to the force of tension, which relating these two equations here, which we just solved for here and here, we can eventually simplify all this out to get that the angular velocity squared is equal to 2/5 times mass times gravity over the mass times the radius. Square root both of those, that gives us our final angular velocity for the turntable itself, being the square root of 2 times mass times gravity over 5 mass times the radius. This here being the big M for the mass of the block, and this here being the little m for the mass of the sphere. Alright, now that we have an answer for the angular velocity, we need to make sure that it actually makes sense. And the first way we're going to do that is by checking our units. So just to start off, we know that the units for angular velocity should be radians over seconds, but since radians are actually unitless, that leaves us just with 1/seconds. Now from the equation we got, which was 2mrg divided by 5mr, all that square rooted, mass, kilograms, gravity, meters per second squared, mass again, kilograms, radius in meters. So kilograms here, both of those are going to cancel out. Mass here are going to cancel out, which leaves us with 1/second squared square root, because that's square root of 1 is 1, square root of second squared is just seconds, which gives us 1/seconds, which happens to be the exact same thing as the units for angular velocity that I just mentioned earlier, which leaves us with 1/seconds is equal to 1/seconds, which means that our answer in terms of units makes sense for what the units of angular velocity.
Another way to make sense of our answer is to plug in numbers and see what we get. So for our first example, we're going to let our mass of our ball equal 5 kilograms, our mass of our block equal 15 kilograms, our radius equal 5 meters, and gravity is 9.8. When we plug those values into our angular velocity that we obtained earlier, we end up with 0.51 radians per second. In our second example, we're going to let little m again equal 5 kilograms, but we're going to decrease big M to 10 kilograms. We're going to let radius equal 5 meters again, and then gravity is again 9.8. When we plug all those values into our angular velocity formula that we get 0.63 radians per second. So what we can see with checking numerically is that the angular velocity is inversely proportional to our big mass. So as our big mass increases, our angular velocity will decrease, which makes sense.
Alright, so for this comparison, I'm going to be comparing the problem we just did to the big spool problem from week 3 lecture. Now, in this case, the similarities between the two are that ultimately we have the same goal. We're trying to find the angular speed of a certain object. In this case, right before it falls off the table. In our case, it was the angular velocity of the turntable. At the end goal, actually, they both have the same units. That being angular velocity, they will both cancel out to be 1/second squared, as radians are unitless. And because this one involves you using the moment of inertia to find that for the big spool, both of them have very similar strategies when it comes to solving them. Now, the main differences are in this case, there's obviously no pulley. The complexity of the systems is very different. This one is just the spool on top of a block, whereas ours had a turntable with a block on top of it, then the block attached to a string, which is attached to a pulley, which is then attached to another spool hanging off of the turntable at the very bottom there. And that, of course, just goes into the complexity of the two. This one, the big spool here, not as complex, very good one to get a basic idea of the concepts here, whereas R1 involves putting together a whole bunch of concepts to arrive at our final answer.
The other problem that we found similar to our turntable problem in this week's project was Activity 4 from Week 4 Studio. Activity 4 was called the Fire Escape and involved a platform moving downward, and it was attached to a pulley by a rope. As the platform moved downward, it was affecting the entire system. In our turntable problem, we had a mass moving downwards that was also affecting the entire system. Both problems could be solved using net force and torque to get the desired answer, but in the fire escape problem, we were solving for a mass, while in the turntable, we were solving for angular speed. Also, both problems had multiple masses present in them, but the fire escape problem was solved numerically, while in our turntable, we just solved symbolically, so we didn't have a numeric value as our final answer.